Okay, hello everyone. Uh, okay, this is the questions last time we discussed, and I would like to just make some notes and emphasis. Do you think it's better if I write in a landscape? This is a portrait, right? Do you think maybe landscape will make it clearer? Because if you see here, it's small, right? So sometimes I need to make this. But if I wrote in a landscape, do you think maybe better? Okay. Maybe next Friday I will prepare the landscape. But for now, let's just take a look. I just want to make sure, okay, what we have done is correct, and my value here is correct. Okay, have you checked? I checked, and it's correct. I mean, not totally the same, but it's supposed to be approximated. So if we compute the sigma f for x and y, you will see that ax is going here, which means in this diagram, the only resultant force that is on x-axis is this one, right? I think the other one, they are not having any force, right? Maybe I need to erase the one and on the top. It's maybe confusing. Let me erase this. It's not the resultant force. Okay. So we can take the AX equal to FBD sine theta. FBD we already count. Okay, 44, and sine theta is going to be on right this triangle, and make sure that we have the same amount of value. The sine is 3/5. Compute, and it's around 26.4. It's 27. Okay, it's approximations. In exam, you can do this. It's okay. That's a method. So if the answer like having a decimals, you want to round the numbers, that's okay. But not too much. Okay, not too much. And then the y-axis. Okay, y-axis. If we look on the resultant, the force is AY, right? And then this FBD cosine theta, and also the 22, right? So AY plus 22 is equal to the FBD cosine theta. Okay? There are no other forces in y-axis. Okay? So I think it's pretty simple. So we just take the minus, and it's around 13.2, and I'm approximating becoming 13 kilonewtons. Okay? That's how we get 13 and 27. Okay. Okay, and then the rest is the same as we discussed last time. So the safety factor is equal to sigma yield over sigma allowable, and we got the allowable is 83.3, and then we got the shear force at A from AX and AY. We take the resultant, like we usually do in vectors. Take the magnitude value of the vectors, and then we got 30 kilonewton around. Okay, it's supposed to be 30 point something. And then later on, we take the shear stress, the tau, and we got, this is from the questions, right? The safety factor 3, we got the 110 megapascal. And then, based on the picture, we know the A, being A is double shear, so we need to divide by 2. So V over A, and then VV over 2A. Okay. And we got the result is going to be, we got the area, and then we got the diameter. Okay. So the same as we did before. Okay. Okay. I think you already right. The last one, right? This is the same like before. Okay. The additional notes is just this one, the sigma f, sigma f, x axis and y axis. Okay, anyone try the exercise? Yeah, the last exercise for the for the statics. Yeah, did you try?
Yeah.
How many questions? All or every question? Okay. How much time you need for each question? Around.
I think
15 to 20, or maybe 30.
should be around
15 to 20. Right?
maybe I would go with around 25.
25 to 30, right? 25 to 30. Okay. And that will be the how much question I will prepare. Okay. But for your first quiz, it will be online quizzes. Okay. It's open notes, so you take your time. But I think after the first quiz, what we want to do next for the chapter 2, 3, and 4, I would like to have like not really a quiz, but it's more like, because we have 1 hour on Friday. So on Friday, I would like to have like it's supposed to be an exercise, but I would like to give you like a set of questions. So it's like a small quiz. It's not as much as the percentage for the quiz, but if you do good, I can consider that as like the small quiz, maybe 3 or 4, I combine, become the quiz 2, if it's good. If not, then just for the exercise. Okay. So I would like to have maybe every Friday, like 2 weeks, every 2 weeks, Friday, I will have like some sort of question, like 2 questions, and then you need to answer. Okay. And I will prepare the questions and give the paper, and you need to work on that paper. Okay. And it's open notes, so you can prepare books, anything. Okay, so this is the questions we've done, and then I've uploaded this one just today, just before the class. Later I will put into the Moodle the video. This is the exercise for the static review. If you have try this, I think the first question. This is the answer that I got. Maybe the differences probably in the decimals, but I think if still similar, I think still okay. Okay. And then last discussion is on this, right? It's on this. So the isotropic materials, that is the assumptions for the relations between the G and E. G is the shear modulus. E is the elastic Young's modulus. Okay, and then we're going to relate the other strain with the Poisson ratio. So let's just imagine, like we did before, you have some material, you apply force, tensile stress, and then it's become longer. But in the other sides, they will be probably have a different value, and we consider the y and z will be the same value for this strain. Then the relations between the strain of in y-axis and z-axis will be equal to the x, but multiplied with the Poisson ratio. Remember, the Poisson ratio is the ratio, or the ratio between the longitudinal and the transversal strain. Okay. And why it's minus? Because you will see that it is actually going to reduce. Okay. It's going to reduce, and the the value itself will be negative, so we need to multiply with negative to make it positive. I will have example on this Poisson ratio later, but before that, let's just take a review on the property of materials in practice. So let's say we have this graph. Okay, so this is a steel alloy cable, the tensile stress strain diagram, and you will see in the x-axis is the tensile, okay. Sigma is in the megapascal. You will see the square is 10, 20, every 10. Okay. And in y-axis, in x-axis, sorry, it's the y-axis is the sigma. In x-axis is the strain, millimeter over millimeter. There are two graphs. The first one is up here. Okay, this is the total graph. Or you say this is the plastic region, while this one here is the elastic region that you are going to zoom in. And how to read this graph is, you see the strain, the first and the second number. The first number belongs to the above curve. Okay, this is the top curve. The second number belongs to this elastic region. Okay. Yeah, perhaps later. I think I haven't uploaded any notes, right? So I think I will upload the notes for you so you can prepare well for the next quizzes. And the specimen for this cable is going to be like this. We have a radius 3 millimeter and then length 250 millimeter. And then later we are going to apply 1000 Newton. Okay. And don't worry about this green color here. I forgot to erase that. That's I'm trying to solve something. Okay. The question is, need to find models of resilience, models of elasticity, models of toughness, the new length of the specimen if 1000 Newton is applied. So there will be applied force, compressive force, 1000 Newton. So the specimen will be shortened, so we become short. Okay, and we need to know how much the new length will be. Okay. Okay. Now for the first one, what is modulus of resilience? What's the definition? Based on the graph, what will be the definition of modulus of resilience? Anyone?
The area under the curve is
which one?
Under the elastic curve.
Elastic region. Okay, elastic region. So this will be, let me write here first, area under the elastic region. So we are going to turn our attention to this triangle, okay, and it's already a perfect triangle, so we can compute this easily. Remember the base, we are going to use the bottom one. Okay. So 0 point, this point means 0 point, okay, I'll make it clear. So this is going to be like this, okay? And this one is 0. Okay, if you are not familiar with this type of writings. So the area under the curve for the elastic region, so the modulus of resilience is half. The height is 40 megapascal. And then the strain is 0.001. So it will be, it will be 20 megapascal divided by 1000. I can make it from millions to 1000 will be a kilo, right? Or you could say still 0.2 megapascal or 20 kilopascal. Okay, and then the second one, modulus of elasticity, or E, is, remember, what's the Young modulus? Yeah, which one? Which one? Yeah, stress over strain, that's true. But which one? Yeah, the lower one. But if I say all here, which need to be specific. Elastic, right? Okay. Need to be specific. If you are just saying stress over strain, it will be not complete. Okay? It can be also plastic, right? Elastic, but the elasticity needs to be in the elastic region, which means the one that has a straight line. Okay, that will be our observation. Okay, this is our main point here. Or you could say every time you have a strain stress curve, if you see something like straight line, the slope is the modulus, okay? The Young's modulus, the slope. Okay? Remember the slope, the gradient. Okay? Remember, if learn calculus, gradient, slope, tangent line, the same thing. This is also the same, okay? Slope. Okay? So we could just take 40 and 0.001. So 40 megapascal divided by this. So multiply with 1000. So it's going to be millions to billions. So 10.6 to 10.9. So it's giga, right? So 40 gigapascal. So I will write here. So 40 megapascal divided by 0.001. This will be 40 gigapascal. Okay, this the third one, the models of toughness. So I'm not sure how the words will resonate with your definitions. I mean, if you see elasticity, it's describing, okay, elastic, right? But resilience. Okay, I think for those of you not familiar with resilience, you could take some dictionary. What does resilience mean? Resilience is when you you stand up, you get a force, and you need to try to make a stand. Okay? So if there's like a wind, you are trying your best to confront the wind, and you still stand up. That means resilient. Okay? Resilient. Okay? That's resilience. That means it's still in elastic. Remember this definition of elastic. You apply the force to the, well, it's not like a Star Wars. You apply the force, but the formation, when you release, it's going back to the normal, elastic, okay? Elastic. But if it's going over the yield stress, it's going to be plastic deformation. You get the force, release, the shape change. Okay, that's the difference. So resilience is how much you confront, okay, or react to the force, but you're still in the elastic region. Okay? And when the force release, you're still going back to the original form. Now is toughness. So how tough the material is. which means tough is related to, like if you are maybe watching like a boxing or any sport that encourage like physicality, we call tough if we can endure all the physical, right? Like maybe if you like watching boxing, or maybe the one that losing is the one that is knocked down, right? It's going to be fail, or in our case in material science, it's failure, right? So which means the toughness is all the energy that we need to make the material fail, which means the energy is all the area under the curve of all the graph. That will be the toughness. Okay? How much we need to make the material fail. Okay? That's the toughness. So this is, let me write, area under the entire curve. Okay. Here, to make it easy, I will do some simple approximations, and I think you can do that too, okay, because there's not much information we need. So we need to have just a simple approximation. So for example, we already know the elastic region from this 20 kilopascal or 0.2 megapascal. So we write that first, triangle, and then we need to calculate the square, the rectangle, right? And then we have this, like in the small area here. Let's do some approximations, okay? So let's say we are going to take the square, okay? We take the square, and let's say the square is 1, 2, 3, 4, 5, 6, 7, 8, 9. It's around 10 square, and then the length, the distance is, if this is going to be 0.005, so probably it's 0.00025 around. Okay? So just a simple approximations. To get better results, actually you need to have, or you need to know the functions, and you can do integration. It will be very, the approximation will be very good. Okay? But if you have this, then what you can do is approximate with geometry. Okay? So you need to just assume and make some approximation that makes sense. Okay? So first, let me write the modulus of toughness. Will be first is the area for the elastic region, which is 0.2 megapascal, okay, and then plus all the rectangle here. So it's 10 square, and then 4 down there. So it's around, and every square is 10 megapascal. So 10, but it's 4, so 40 and 0.0025. So we can write for the rectangle, this is okay. Or you could say from this 0.001 and then 0.0035 is 0.025, right? So this is from I need to be add another 0, right? Okay, and then multiply with the 40. The second one this is for this big rectangle, okay? And then we have a small small sections there, okay. And then my assumptions, okay, because we're not sure how much this is. You can do two options. You can make it like a triangle and assume this is going to be, let's say, if this is 10 megapascal, maybe this is around maybe 3 or 4 megapascal, and then multiply with the distance, and then multiply 1/2. Or let's say this is we have. So if we add all these things here, because it's going to be small, I assume this 10 square. If we add this triangle here, if we add all the area, it will be 1 square. Okay, that's my assumptions. Okay. Okay, assumption is it can be okay. Okay, if the questions doesn't give you necessary information, so you can assume. So assume 10 square is total triangle, which means this triangle here. Okay. So if you add all those area, it will be 1 square, or maybe this is not 10 square, maybe 1. Which means this is 1 square. Total triangle 10 area. That's what I mean. So 10 area. Adding, and it become 1 square. So 1 square is the height is 10 megapascal, and the distance is the same. Oh wait, this is it's another 0, right? 0.00025, yeah, and then multiply with 10 megapascal. And then the last one, we need to plus the plastic region. So this is supposed to be, let me write here, plus the plastic region. Now the square, the length becomes, using this 0.04, okay, and then 0.08. The middle one is 0.0, let's say this is 2, yeah, 0.02. So the length for the square in the plastic region is 0.02. So we need to add all geometric, okay, the square, and then also approximate these sides here. Okay, approximate. In my approximations, this is the total here is around 92. Okay, 92. It's also including the one that is going to be here, so it's going to be 92. Or if you just want to calculate there, maybe you could calculate. Well, anyway, it can be any square. It depends on your assumption. So this is going to be plus 0.2 multiplied by 10. This is the square. And then in my approximation, this is going to be around 92. This is total total square. This is square area. Okay. And this will around get you the result around. But again, this is approximation. It can be different approximations. The more clear results, if you have clear functions, that will be easy to follow. If not, then perhaps it will be based on the geometry. Okay, the fourth questions. Okay, the fourth questions is the new length of the specimen. So the specimen will be applied force, compressive force, 1,000 Newton is applied to the specimen. Of course, the length will be shortened, but how do we know? How do we know, and how do we apply that? So first, what we can do is, we know the force, we know the area, so we know the stress. So that's the one that we are going to take. So the force or the stress, in this case, the stress applied is, let's say, P over A, this is 1000 Newton, over pi, this is 3 millimeters squared. Okay, let me check whether my approximation is true. Okay, 35.37 around. It's mega Pascal. Okay, so I think it's Newton. Every time you have millimeters squared into familiarize yourself, it becomes mega Pascal. This is very for almost the case, for most of the solutions. This relation will be, you will see often. You will see often. And then where is this stress from the picture here? So if you see 30 and 40, it's around here. It's still in the elastic, right? It's still in elastic. So we are going to use this information to get into the strain. What will be? Okay. So let's say this blue one here is our 35. So we could take this, okay? So let's say this is our x, okay? So according to the elasticity, we can take the definitions, x over 35.37 equal, let's just say 40 and make it the strain 0.001. So this will be 0.001 and 40. Okay. And then you'll get x is around, let me check my answer. It's going to be 8.84 multiplied with the 10 with minus 4. So it's around 0.00884 millimeter per millimeter. This is strain, right? Okay, let me write here. This is strain, okay? Remember, the x you get is the strain. It's not the length. Okay, sometimes you think maybe this is the length, and then you are minus this with the length. But we are not over yet. We need to multiply with the length so we know the total. Okay. So remember, the strain is delta L over L, right? So if we know the strain and we know the L, then we can calculate the delta L is the strain multiplied with the original length. Okay, the original length, as we see from the specimen, is 250. So the strain multiplied with 250 millimeter. So let me compute this, and the delta is 0.221 millimeter. So the new length is the origin length minus delta L, or 250 minus 0.221, or this will be minus 249.77 millimeter. Okay. Oh, why I'm writing minus, sorry. Not minus, it's positive, sorry. Okay, so don't forget that you get the x. This is still strain, not the length. So you need to multiply with the strain formula, get the delta L, and then you can subtract the delta L, and you get the new length. Okay. Okay, now this is about the stress strain curve and how to define some of the property. Okay. I think in the last chapter, maybe near the last chapter, there is some specific chapter about the energy. How do we look energy is the same when we look this modulus. It's actually the energy that will be used. Okay? And we can also use that for our mechanics calculations. Okay? We call that the energy method. But I'm still not sure whether we are going to go that chapter or not. But I will focus in the first 4 chapters. That will be really basic on mechanics. So let's go to another problem. Okay, so I would like to start the course today giving you 2 problems. The previous one is a stress strain diagram. This one is related to the Poisson ratio. Okay, so let's see the picture here. Okay, so you have a beam. It has an 80 kilonewton force, and then it has this specific material. Yeah, I've given the elastic modulus is 73.1 GPa. That is for this aluminum, 2014 aluminum. Diameter is 30 millimeter. You have a column A and column B with different height. Okay, with different height. You have the distance, total distance, AB is 3 meters. So if the beam is to remain horizontal, so the beam is still intact in a horizontal position. Okay. Find the distance x where the 80 kilonewton must be located. So we need to know where this 80 kilonewton to be located, so that the beam is horizontal. Okay? And then it's also asking the new diameter of the column A. Okay. So if you could visualize what will happen, so we have a force going from above. This column is pressed. When we press this, it becomes shorter. What's the impact? What's the consequence if this is becomes shorter? So let me draw here. The impact will be, so if this is the original length, okay, and if this is going to be having a force like that, then let's say this is the new column, okay, so it's become wider, right? Can you imagine that? Like you can imagine like a jelly, you push the jelly, but it seems like getting large, okay? So that's why there will be a new diameter, okay? Okay, so quite complicated. But first, what should you do? What should you do? You are given this question. How to identify? Any idea? What should you do? Oh, I already mentioned some formula here that they will be using that formula. Okay. But what should we do first? What should we do first?
Should we identify like all the there should be like support reaction?
Yes, external force. So it's ideal for us. If this picture may be a little bit complicated, maybe we need to focus first. Let's just focus on this beam, okay? Because the beam is going to be our assumptions. That is, it needs to be horizontal. Okay? So it needs to be the same. So when this going down, the B also going down. So it's remain horizontal. That's why I'm writing on the left side. If you take some notice here, the delta A is equal to delta B. Okay, so which means the height, if it is going down X or maybe Y, this is also going down Y. Because we need to make sure it's going to be horizontal. So this is the first assumptions. And then, since we have this beam, so let's draw the diagram. So let's just maybe make it clear. Okay. So let's say this is the AT. And let's say on A and B, we are going to have, let's say this is FA, we have FB as the resultant. And then the distance, we have the distance, okay? We have the distance, 3 meters, right? And then the X, this X here. Okay, first is that. And then of course, can we solve this? Can we solve this? This is our questions here. We don't know A, we don't know B. So we're not going anywhere, right? So we need to do something about FA or FB. We need to find some relations. So how to find the relations? Remember that? The assumptions, okay? We're first going to the having the same here. So the difference in length is what related to what formula? Yeah? Yes, strain. Okay. So strain. So we are going to take first is the strain is related to the delta, right? Let me write the formula first like that. So the delta is equal to this, right? So when we say the delta, let's say L, maybe this makes confusing. Like maybe let me write in L, okay? LA, LB, maybe better, okay? So the delta L, delta LA is equal delta LB. Okay. Okay, let's have a break first. Okay. Okay. Okay, now we continue the calculations. So this is assumptions we have. Okay. So then we can rewrite into our strain multiply with the original length. Okay, and then we also remember and we write all the formulations that we have. This is E is sigma over strain, right? So the strain is sigma over E. So we are going to change this strain with the sigma A over the modulus elastic, and then this is also the same. Okay, so the modulus elastic is the same for both because they are both in the same material here, right? So we doesn't really need to calculate this number, so we can just cancel it out, right? So we can just take this out. Okay. Okay, and then the sigma is F over A. So we could take that and write here becomes FA over AA, LA, and then FB, AB, LB. And the area, since they are also the same diameter, you could also cancel, right? So cancel, cancel. Okay, so let me write here, this is because this is the same, and this is also the same. Okay, so we are just taking FA and FB based on their height. Okay, the height is 220 and 210. So let me write here, FA multiply with 220 meter, and then FB is 210 meter. Okay, so we could write FA is how many times FB? We get this 210 divide 0.945 FB. Okay, with these relations, it's enough for us to get to know the FA and FB. Okay, because we know that the sigma F for the y-axis, this is going to be FA plus FB equal to 80 kilonewton, right? Or let me write, maybe right on the left side here. Okay. So since FA is 0.954, so we could just plus 1, so we could take 1. This is FB, and this is going to be, okay, so 80 so 40, so FB is 40.93 something. Let me just write kilonewton. And FA is 80 minus FB. This is equal to, so we could take minus 80 is 39.06 kilonewton or 07. Okay, now because we know the F for FB, we could find the distance now. So you could take the sigma moment, okay, sigma moment. You could take with respect to A or with respect to B, but I would like to get the direct answer, so I would just take the A. So we are going to take the moment, take here, and then take there, right? So you could take, maybe let's make that positive. Sometimes I do counterclockwise, sometimes I do clockwise, doesn't matter, okay? I hope you are familiar with that. So let's take the sigma moment, A equals 0. So FB multiply with 3, and then minus 80x equal to 0, right? So x is 3/80 multiplied with this, right? So it's going to be 1.534 meter. So that's the locations for the x, okay? So it's around the middle, right? Around the middle, because the total distance is 3. So this is for number A, number A. Okay, for number A, any questions? I think the important things is getting these relations. This is very, very important. If we do not get this idea, we are going to have some difficulties deciding the rest of the solutions. Okay, the second questions is the new diameter of the column A. I forgot to mention that within this material, okay, if you check the Poisson ratio, that we are going to use that, the Poisson ratio is going to be around 0.35. I forgot to mention the information. So we are going to need this Poisson ratio to get the approximation on how much the diameter will change. Okay? Because the Poisson ratio is the ratio between the longitudinal and the transversal, okay? The strain. So the change of the transversal and the longitudinal. So this is the Poisson ratio. Okay. Okay, because we are going to take the column A, then we are going to need this FA. FA is, where is FA? This FA. Okay, this is FA, right? Okay. Now, so for number B, since the Poisson ratio is 0.35, and we can calculate the sigma A from FA divided by AA, right? The FA is 39.07 Newton, kilonewton, sorry. Divide, this is pi, and then we have 15 millimeter, right, squared. So we are going to have the kilonewton over millimeter squared, or we could change the kilo to Newton, so you could directly get the MPa, the megapascal. So we could take the 39 is around 55 55.27 MPa, megapascal. Okay, now from this megapascal, this tensile, we get the E. Okay, E is sigma A over strain A. Okay. So from the tensile and then the modulus elastic that we have, we are going to get the strain A, which means strain on a column A. When we have the axial stress, this will be the longitudinal, right? The longitudinal length, right? So this will be the longitudinal. Let me write long like that. So we could take the computations and we take this as divided by E. Okay. Now the E is 73.1 GPa. So let me write in the megapascal. So 55.27. And then 73.100. This is MPa. So divide. Strain A for that is longitudinal is equal 7.56 with power of -4. But remember, the strain that we have is that from the compressive, right? From the compressive. So because the compressive, if you remember, the length will be shorter, right? So it's supposed to be, in the calculation, it's supposed to be, we write the negative. I forgot to write the negative. So this is going to be having a negative here. Okay. 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 Do you get why I wrote the negative? Because if you remember the strain, let me write here. Well, let me write in the new page, so much more clearer. I hope everyone already write all the components. So let me copy this part. Copy. Let me write here. Okay. So remember that the strain is coming from the delta L over L. Okay. If it is tensile, it's no problem. But if this is compressive, then the delta, it's supposed to be the new length minus the original one, right? What happened with the compressive is the new length is shorter, right? It's shorter than the original length. That's why it's become negative. So that's why we need to write here. This is also becomes negative. This negative comes, or because the stress is compressive. Okay, because this is negative, then from the Poisson ratio, we could find out the transversal, the strain that is in the transversal axis. So this is longitudinal, this one, the transversal is this one. Okay. So let me write the Poisson ratio. Not like this, supposed to be, not really. Well, like this, I think it's okay. This is going to be negative of lateral divided longitudinal. Okay, that's why we have the negative here. Do you know why now? Okay. This is because this compressive. So we need to make sure that the result is positive. Okay. So the strain lateral now is multiplied with the longitudinal. So this will be multiplied with the 0.35. So negative 0.35 multiplied with the longitudinal is negative. So this will be 2.646 millimeter over millimeter. Okay, and this is positive because it's become wider. Okay, and again, this is not length, this is strain. To get to know the additional length, we need to multiply with the original length. Okay, the original length for this one here, the length is on the transversal axis. So which means this diameter is the original length. Okay, so let me draw here to get you. Okay, let's say this is the original. Okay, the original. So this is A. Okay, what's happened is we get this compressive, so it's become shorter, and the diameter becomes wider. Okay. So this is the original diameter is 30 millimeter. Now we have the delta of the diameter is the strain lateral multiply with the, or let me write with directly with the original diameter, which is 2.646 multiply with 30 millimeter. Okay, so multiply with 30, this is going to be 7 millimeter. Now this is the delta. The question is asking the new length, the new diameter. So the new diameter is the diameter plus the delta. So 30 plus, so it's only like a few small millimeter. So 30 plus 0.007, right? So 30.00793 millimeter. Okay, so this will be the new length. Remember that this is lateral, this is longitudinal. Poisson is lateral divided by longitudinal. May write to give you more descriptions in your note. This is the new length. This is the okay. Now I believe that is for reviewing the shear strain diagram and the Poisson ratio, how to apply and how the example. Okay. The next is I will skip this one and I will making this part here just an additional video. Okay, this is actually how to relate E and G. What's the formula? But I think I take time too much in class. Not really good for our course. So I will just put into additional information. I will focus from the weeks by weeks later. We are going to focus more on reviewing the tutorials. Okay, so I will get into like more emphasis on how to solve some problem. Okay, so I'll skip this. This also I will skip. I will make another video. This is this is just a theory that is related to a concept that is not really practical, but we are going to need this at least to relate to the real life situations. Okay? But what we are going to do mostly in the problem solving, the questions is a simplified question, so we don't really get into. But if you are have an interest to know how we deal with the real life, then you are going to need some simplification like this limit, okay? Because we are going to take some calculus in the process. But this is more in theory, okay, like this one here. This is more in theory. In practice, of course, we basically mostly do approximations, okay? But if we know how to simulate the function, then perhaps the integral will be a better choices for our calculations. Okay? But this is, I think, for more on theory. This is also the same. I will make this into another formulation. This is about the shear strain. Okay, how to look on the differences. Okay, how to see the differences in the angle as we give the shear strain on the material. Okay? So we are going to see the change in the angle. Okay? So I will move on to the chapter. This is chapter 3, the axial deformation. So let me get into the point. What is the assumptions? Okay. So of course, from the words, axial deformation. So which means there will be some deformations in this axial axis, or in one axis there will be some deformations, and we are going to see how we are going to deal with that. So assumptions, first, axis of the member remains straight. Okay, which means that if we are going to take some deformation, it's still on the same axis and it's not going to bend. Okay, it's not going to bend. It's going to be still the same straight positions. And the second, at the cross section, which are planar or plane, and perpendicular to the axis before deformation, will remain plane and perpendicular. So two assumptions. So first, the axis is remain straight. The second, the cross sections, if it's having the deformation, is still the same cross sections. Because in the real life, okay, so aside from these assumptions, if we maybe make stretch, maybe the cross section get bent, right? But here in practice, in how we simulate, we are making assumption that the cross sections, if we maybe take some stress, it's still same cross sections, okay? And still perpendicular to the force. Okay. Let me maybe get you some drawings, or maybe here, okay. to give you more context. So there will be some L, the length, and then you put some force, you pull, having a tensile. It's getting longer, but it's not going that way, right? So we need to assume it's still straight. And then this cross section here still it's still in the perpendicular with this. It's still here. Well, of course, there will be some additional length. That is the deformation that we are going to calculate. This new length A asterisk BS. This is the new length. New A, new B. Okay. That will be the deformations. So that will be our focus. Okay. So before deformations and after deformations. And then from this small displacement delta x, we could take the strain formula on x-axis, which means strain on x, as a function of x, let's say. We could take, let me write the limit first, okay, just to make sure we are have the same theory. So as the delta x going to be 0, or it's going to be really, really small, okay. We are going to take this new delta x minus delta x over delta x. So this is going to just focus on the difference on this delta x. It's getting larger, okay? So this will be our focus. Then from this u x plus delta x, and this is also ux, we could rewrite the delta x, okay, as the ux plus delta x minus ux. Okay. This is just to give some confirmations or the relations with the differential or differentiations, if you remember, if you still remember calculus. Okay, so here we have that delta x is, if we take, this is another function ux, okay. So this is ux plus delta x minus ux, right? Well, in calculus, remember that you have the f, x plus h, right? Minus f of x, right? No, this is just a theory, okay? Just a theory for the limit, okay? In practice, we are using directly. Okay? This is just to show you that we can rewrite the limit using the u and divided by delta x. And this is actually the derivatives, right? Let me write if, let me write here. Just to make notes, let me write with green. Let me write here. So that is if we have the f prime x, this is limit as h, or maybe delta x, or maybe h, if you remember. This is fx plus h. This is the definition of derivative, right? So the same thing here, that we can conclude that this is going to be d dx of u, or we could say du dx. So, at the conclusions, the axial strain at section x, this section x here, is derivative of axial displacement. So we could write the strain is we say that this is the strain displacement equations. So what does this equations emphasis? This gives you conclusion that axial deformation is only characterized by the extensional strain. So this is to relate that this only this extensional strain, the delta x. Because if we think on perhaps look at the cross sections that maybe the cross section can also be a function of x, right? And we think that that is also a variable, then our relation will be really messy. Okay? So it is to state that when we have this is only on the extensional strain. The deformation is only by the extensional strain, not the function of the cross sections. If you don't understand that, that's okay. So, okay, now if you look here, yeah, this is what is the extensional strain distribution for a member or material, okay, that undergoes the axial deformation. Okay, and then another part that is I'm going to emphasize is the elongation formula. Okay. Now if you look here, if we take that this is before deformation, this is after deformation. So we are going to characterize. So all the points, there will be a new points, okay, after deformation. So it will be, so the original point will be shifted. Okay, they will be shifted, and it's become longer in distance. And then we have a functions here, okay, a functions in terms of for the displacement, and we take the elongation formula, okay, as a well. If you see the what we have before, is actually just we reverse the previous equation. So if we'll take this strain, that this is going to be du dx, we are going to take du equal. Okay, this is basically what does it what it says. Okay? So if we want to take the complete elongations, so we can integrate. Okay, we can reverse the derivative formula, and we take the du and we write as e for the total elongation from 0 to L. L is defined as the length at the beginning. So we take the integrations from both of these. Okay? I think this better approach. Okay, if you maybe not really understand on the picture here, but we could also understand from those picture and looking at the this UL and then U0. This is, if you remember, this is pretty much calculus, but change the variable with the U and E. Okay, that's the net theorem for the integrations. But anyway, okay, what else do we have? Oh yeah, just a small sections on the conclusions. Okay, what we have. First is still we have the Hooke's law. That is the sigma now x equal E and then strain of x. Okay, and then all the assumptions will be similar to what we have before. We need to make sure that this assumption is for the uniaxial stress. Okay, and then the stress resultant, this is for this picture here. So the stress resultant based on all the forces that is mentioned on the left. Let me write just the conclusions. So for the f of x, this will be the integrations, okay, sigma and dA. It is going to be taking the double integral. Okay, the moment of y, okay, and multiply with x. This is integrations. This now is z, sigma, and then dA, and the moment of z. This is y, and for z, since the moment y is positive, the z should be negative, right? It's going to be negative. Well, if this is positive, then the my is negative. Okay. And then another important thing on this Hooke's law, this E. Okay. So when E is constant, then stress distribution is constant. Similar to strain distribution, that is also be a constant. Okay, this picture is going to be here actually for the stress distributions, and the picture is going to be here. Okay, this is resultant force and resultant force. Okay, I will end until here. Okay. Okay. Okay, I think we finished until here. We're going to continue on Friday. And for your quiz, you can just keep update on Moodle. I will attach the quiz, the links. That will be an online quiz. I hope you take the exercise, try to work on the exercise. The quiz will be open notes, so you could probably prepare books or something. Okay, I think that's all. So see you on Friday.